So, we are getting down to the wire. To recall from where we were last time, we were talking about reliable message delivery. And a couple of things to note before we sort of dive into some of the details of TCP are, number one, physical networks can basically drop or garble packets. You've got to keep that in mind. And I gave a couple of good examples of why that could happen. So one, there's a big interest in basically transmitting as fast as possible because that gives you a higher bit rate, but that, as you're kind of right on the bleeding edge of speed, you can start dropping packets. And there's kind of a happy medium there you want to hit between getting things out faster but not dropping too many packets. And another example here is trying to save energy by lowering your voltage until you're just at the point where you start losing bits. Okay, and once again, you want to trade off not going too low because then you get too high of a delivery loss. So these are two types of optimizations people might want to do on the physical media. You know, physical media in general can be lossy for lots of other reasons as well. So that's one reason we might garble packets. And congestion, which we'll talk about today, is another reason that packets could get lost. And this is an example in a point-to-point network where you essentially send data and there's no queue at the destination because they're all full. What are you going to do? Drop the packet. Okay, and this is pretty much the standard thing that they do in TCP/IP. And so these two possibilities here lead us to at least have to assume that packets could get garbled or they could get dropped, and we got to make sure our protocol deals with that. Notice also that it's possible for packets to get reordered. Okay, so these are all potential problems. And so in order to get reliable message delivery on top of unreliable packets, we've got to do something. And in particular, we've got to make sure that every packet makes it there once and it makes it there only once. Okay, why do we want to make sure it gets there once? Well, we want to make sure that the things we're transmitting actually show up. Why only once? Well, because sometimes the arrival of a packet may do some action, and not all actions can be repeated properly. Okay? So, and we can combine, as you'll see in a moment, techniques for dealing with reliable delivery with techniques for reordering packets that are misordered, and of course that's going to lead us to using sequence numbers. Okay, were there any questions about this basic problem statement here before we dive in? We good? Okay. So today I want to finish up the discussion of TCP/IP, which will be useful for your project. Actually, TCP/IP has many more features to it and sophistication than what you're doing in your project, but we'll give you flavor for what the full TCP is like. And then we'll talk about messages as a general programming paradigm, which is a little above the packet level. And then we'll talk about some distributed decision making, things like two-phase commit and Byzantine commit. And I don't know whether we'll get to remote procedure call this time or not. Okay. So how do we use acknowledgments? Well, very simple, right? You send a packet, and the other side acknowledges it. Okay, now, end of story, right? Well, of course, it isn't quite the end of story, because what happens if something's lost in the middle? So, for instance, if the packet gets lost and it never shows up at B, at some point, A will say, gee, I didn't get an ACK. And there'll be a timeout period after which it says, well, it must have been lost. It'll retransmit the packet. It'll eventually get the ACK. And now the sender is happy, and the receiver is presumably happy because we know it got the packet. Okay? Notice that this timeout is ideally triggered on the time of the original packet send. So basically, when you send the packet off, you somehow start a timer here, and sometime later, relative to the original sending of the packet, then we retransmit. Okay, and the reason we want to have that kind of offset there is really because we're going to try to tune the timeout based on how far this packet has to travel, because we want to have just enough timeout to recognize a lost packet without waiting too long to correct a lost packet. So it's kind of a fine line there. All right, so some questions, of course, that we asked last time. So if the sender doesn't get an ACK back, does that necessarily mean that the receiver didn't get the packet? No. Okay, so this is kind of funny, right? You have to deal with the fact that you may have sent a packet and it did show up. He sent an ACK back, that didn't show up, right? So it's possible that the sender actually did get the packet. So we want to make sure, and this is where duplication clearly comes into play, we got to make sure that B can recognize when it gets the packet twice. Okay? And this is basically what happens if the ACK is dropped or the message is delayed. So that's another interesting thing. Suppose that we've got two completely different paths to the destination. Packet A, goes to Florida by way of Australia. Okay, it's possible that that's a very long path, or it gets stuck in a loop or something for a little bit, and then we retransmit, and then it shows up. Okay, so it's possible to get duplication just because of delayed packets. So, sender doesn't get ACK, retransmits, receiver gets 2 packets, and potentially we've got a problem. Okay, everybody with me on this? Okay, so how do we deal with duplication? So notice, by the way, that the timeout is dealing with loss here, right? So the fact that we timed out and retransmitted means that we eventually show up at the other side. So now what we're going to talk about is how do we deal with the case where the packet actually went twice. And, solution is a sequence number. You basically put a sequence number in the message to identify which packet it is. And if you get a packet with the same sequence number, presumably you've gotten a duplicate. Okay? That seems simple enough? Okay, now of course the trick is how do you manage the sequence numbers, and we'll get to this in a moment. But for instance, what are some of our requirements here? Well, certainly the sender better hold on to any messages that it hasn't officially got an ACK for, and the reason for that obviously is it needs to retransmit them. Okay, the receiver needs to keep track of all possible duplicate messages so that it can throw things out. Okay, so it's really easy to figure out, what things aren't ACKed. It's a little harder to figure out when to forget about a received message because there are any number of circumstances whereby you could get the message twice or 3 times or 4 times. So how do you know when to throw it out? Okay. So here's one possibility. So let's start simple and always start simple, and if that doesn't work, then you go complicated. So suppose we have a simple protocol with 1-bit sequence numbers. Okay, we call this the alternating bit protocol for obvious reasons. And the idea is you only send one message at a time. You put the sequence number in it, which is either 0 or 1, and you get an ACK back with the 0 or 1. And the sender basically keeps the last message that they sent. So that's the size of the queue on the sending side. And the receiver basically only needs to remember that it's already seen packet 0. Okay, and when it finally gets packet 1, then it can assume, maybe we'll violate that in a moment, that packet 0 is done with, and it can stop thinking about packet 0 as a possible duplicate. Okay, so very simple. So the pros of this particular algorithm, it's very simple. The overhead is extremely small. It's 1 bit. So what are some cons that might show up here? Yeah. Yeah, big con. You can only send 1 packet at a time. Why is that bad? Why is it slow? Yeah. Yeah. Well, basically you're not filling up the pipe between here and your destination, right? And so basically every packet requires a complete round trip to be sent, and that's going to bring your bandwidth way down. So ideally, we'd like to have a lot of packets in the pipe to make up for however big the pipe is. What are some other problems here? Anybody else? Go for it. No? Okay, so you're going to object to the amount of bandwidth to send the ACK packet. Okay, I might buy that. We're making you waste all that bandwidth on Project 4. We'll show you how TCP fixes it, but okay, I'll buy that. What else? What happens if a packet is delayed? If packet 0 gets delayed for long enough, and then you eventually get back to sending packet 0 again, it's possible that an old packet 0 and a new packet 0 could look alike. Okay, so you have to know how long is it possible for a packet to actually be stuck in the network and show up at the other side. All right, so this protocol is very poor performance and doesn't deal well with network delay. So what's the obvious thing? Yes? More bits. Okay, give me more bits. So yeah, so this is actually called a windowing protocol. And this is not quite what TCP does, but the basic idea is pretty simple. We have up to n packets that can go out without an ACK, and n is a number that's going to be adjustable based on distance. And each packet that arrives potentially sends an ACK back. And once the ACK arrives, then you could resend a packet with that sequence number. So notice in this case, I've got basically 5 valid sequence numbers, and I start reusing them as soon as I've gone through all 5. Okay? Now, the nice thing about this is this sort of serves a dual purpose. So the first purpose is it gives me this reliability of knowing the packet's actually arrived. The second thing is it gives me ordering. So, for instance, if packet number 1 shows up before number 0, I know there's an ordering problem. And I could potentially say store 1 here and wait for 0 to show up, and then I can have both 0 and 1 sent back to the user at the receiver side. Okay? So what happens if the packet gets garbled or dropped? Well, what that really translates to is, as I just mentioned, some ACK doesn't show up. So maybe I get ACK 0 and 1, 0 and 2, 3, 4, 5, and I don't get ACK 1. Well, that tells me exactly what I have to resend, which is packet number 1 got lost. Okay? And notice that the timeout in this case is relative to when I originally sent the packet. What happens if packets arrive out of order? Well, we could throw them out. So if I ever get a 1 before a 0, I could throw it out. But in this particular simple protocol, it's very easy to tell kind of which ones I don't have, and you can actually just send it back to the sender and say, well, gee, you know, I'm acknowledging 0, 2, 3, 4, 5, but I don't have 1. You can send me just 1. Okay? So, you know, the alternative is obviously just what I said here. You hold on to the ones you've got, you wait till the one that's missing shows up, and then you send everything in order to the receiver. You know, what if the ACK gets garbled? Well, now we just retransmit. The nice thing about that is we know it's been retransmitted because we know we got packet 0, and we can filter it out. Okay? Now, this, if you think about it a little bit, is starting to get a little on the edge if we're reusing things right away. So in fact, ideally, we'd really like to have an even bigger sequence number space than the number of outstanding packets. Okay? Questions? Yeah.
So the reusal of the sequence numbers.
Yes.
Right? So if the receiver acknowledges that it got, say, packet number 1, will the sequence number 1 be reused immediately?
Yeah. So as I was just mentioning here, we probably want to have more bits than just the number of things outstanding, so that we don't get confused about reuse versus an old duplicate packet. So indeed, here we got ACK 0, and what we do is send out packet 6 at that point. Okay? All right, good. Now, let's talk a little bit about, so any questions on the windowing idea? There's some clear questions you could ask here, for instance, like how do I know that there's queue space at the destination? So if a packet shows up and the queue is full, we throw it out. Okay. So that's certainly plausible. Now it seems like that's an instance where dropping a packet is probably undesirable, right? Because both the source and the destination know how many packets are outstanding. Wouldn't it be nice if we could actually reflect the size of the queue back to the sender in a way that doesn't require dropping packets at the destination? Now, why does that not contradict what I said earlier about, well, if a queue fills up, you just drop things? What was I really referring to? Anybody see the distinction here between Source, destination, and other. What about other? Well, there's a bunch of things in the middle here, and if I fill up queues in the middle doesn't have any knowledge of source or destination, can't do anything about it, and that's the point at which you start dropping. Okay, but we'd like to be able to have a protocol where source and destination kind of agree on how much queue space there is. Okay, question? Yes? Yes. So part of the negotiation when you start up the protocol, as I'll mention in just a moment, has to do with saying how much queue space you've got. Yes. Okay. So what is TCP? So last time we talked about UDP. And all that UDP is it's like taking an IP packet and wrapping it a little bit more in a way that allows you to send from process to process. But by and large, it's still just a datagram packet. So it's a chunk of data that you send as a chunk. It arrives as a chunk, or it doesn't. It gets reordered as a chunk. TCP is a little different. No packets are visible at all to the user. It's really a streaming protocol. And the idea here is that I dump some bytes in on one side. They show up on the other side. They show up in the same order I dumped them in. They show up reliably on the other side. Okay, that is the what we're going for here. Is everybody with me? So notice how I dumped A, B, C, D, E, F, G, over here they're going to come out A, B, C, D, E, F, G, H, I, J, K, so on. Okay, in the same order they were sent. No packets are visible, so the user doesn't have any idea what packets are underneath. So, and it's reliable. So if things get somehow dropped in the middle, the user doesn't have to worry about it because the program, the process on either side doesn't have to know about retransmissions or anything. So we're going to hide that underneath an abstraction layer. Okay? Now, so TCP is basically IP protocol 6. It's layered on top of IP just like UDP, but it has a lot more that's done. And it's basically, like I said, it's a reliable byte stream between two processes on different machines, possibly over the internet, doesn't have to be. The details are, takes the input stream, it fragments it into packets, which then sort of zoom across the internet, and they show up at the other side. What's interesting that you may not realize is, so obviously there are packets underneath here, but it's possible if the MTUs change, remember the maximum transfer unit, that you might have started out on this wire with packets of size 1500. They go through this router, and on this wire the packets can only be 200 in size. At that point, IP will actually fragment things from this router potentially, chop those big packets into small ones, and now you've got what are called fragments, which are pieces of a TCP or pieces, of an IP packet that have been chopped up by the router and typically have to be reassembled at the destination side. Question? Yes.
So then, like, with the if there's a problem with would it? I think it's the answer to my question. But say the packet gets a fragment of the packet gets dropped.
Yes.
The whole packet would have to be resent, right?
Yeah, so if you lose a fragment of a packet, it's possible the whole packet has to get resent because the protocol at either side only knows about the original packet size. So that's one particularly good reason why you'd like to first figure out what the smallest size is and only chop into smallest size packets at the source. Okay? Yeah, question?
Suppose the packet is going through two routers with different sizes.
Yes.
Fragments once and then it fragments again.
Yes.
But my understanding is I only have one fragment.
Yeah, so basically you start getting into trouble if it's fragmenting multiple times. I think it starts dropping things at that point. So basically there is a do not fragment bit which you can use to sort of sniff out a path and sort of slowly lower your sizes until you find kind of a good minimum size that makes it all the way through.
But IP might decide to reroute anyway later.
True. So it's all heuristics, but it does pretty well. So how do we get things to be reliably and unordered from point A to point B? Well, we're going to use a window-based acknowledgement protocol, and it's going to minimize the state at the center and the receiver in a way that I'm going to show you. The window is actually going to reflect the storage at the receiver. So we're going to keep track of how much queue space is here at the destination so that the source doesn't send more than could reliably arrive at the destination. So let me explain that a little bit more. Suppose you've got a process over here that's receiving, and all of a sudden it stops. Well, it will never be the case with a proper TCP protocol that more data will be put into the network and in flight than could be queued. Okay, so it'll actually make sure that even if the receiver stops receiving, that everything in flight will actually properly arrive and not be lost. So that's kind of the optimization it tries to do. And we want to make sure that the total amount of data that's in the network reflects how much data could be in the network. So we want to actually pick our window size based on latency. Okay. And then automatically retransmit lost packets. And finally, if it turns out that one of these routers is badly congested, because many things are transmitting here, then what we want to make sure we do is slow down automatically so the router is not overloaded. That's called congestion management. And this is why when I say TCP is a good citizen, it's a good citizen because it tries to make sure that nobody is dropping packets from being overloaded. Okay, so if this router is only being used by one stream, you get one speed, and as other things start using this router, things will slow down, and your stream will automatically slow down to match the bandwidth of the router. Okay? That's called being a good citizen. How do you get that number? Well, it turns out what you can find out is you want to have an amount of data outstanding that's just at the point below where you stop dropping packets. And so it kind of automatically adjusts the window size based on packet dropping. Okay? And it turns out that the way the TCP protocol works, it'll also open the window up when the router starts becoming uncongested. So it's automatically monitoring the loss. Okay, so how does this work? So on the sender side, we have sequence numbers. Okay, now these sequence numbers are representing bytes, okay, not packets. So that's a first major change from what I showed you earlier. TCP sequence numbers are about bytes, not packets. So what we can say is, think of the data that's going from source to destination as this continuous byte stream, and every byte has got a sequence number associated with it. And now we can divide the sequence numbers into three phases. Kind of those who have been sent and acknowledged, those bytes that we sent and acknowledged, those that have been sent but not acknowledged, and those that have not yet been sent. Okay, so that's three different regions of sequence number space. Okay, now, I did not say that every byte gets an acknowledgement packet. I did not say that. Okay, in fact, I explicitly do not want to say that. What I did say was every byte has a sequence number. Those are two different things, and I'll show you in a moment what I mean. Okay? Now, what do we see in the destination? We see something similar. The sequence numbers at the destination kind of get divided up into three phases as well. We have those which have been received and given to the application, those which have been buffered and not received, and then those not yet received. Okay? And of course, a byte that has been received has a sequence number that might be in one of these two phases. Okay? All right. Questions? So the same byte gets the same sequence number at source and destination. So here we go. So what we're looking at here is how TCP how it works. Imagine we're at sequence number 100. Okay, and we're about to send a packet. So first thing is, from previous transmissions, we will have an acknowledgement that says we are at sequence number 100. And this is back to the sender, and there are 300 bytes of storage at the receiver side. Okay. Now, suppose we try to send a packet. Now, what I mean is, the user puts some bytes into the input socket. TCP divides it up into a packet, and for instance, in this case, it divided into a packet that is of size 40 and whose sequence number starts at 100. Okay, and that packet goes to the destination. Now our sequence number at the destination is at 140, right, because we received 40 bytes. And notice the acknowledgement that came back is simply says, I'm acknowledging sequence number 140, and there are only 260 bytes left in my queue. Okay, so notice how with a single acknowledgement, I acknowledged 40 bytes that went in a single packet. Okay, so I'm not putting an acknowledgement for every byte received. Okay, are there any questions on this so far? So now if I send another packet, here's one where there's 50 bytes to send. Notice that the sequence number is 140. Why? Well, because these 50 bytes start at sequence number 140. The size is 50, and what comes back for an acknowledgement? Well, I acknowledge that I received up to 190, and there's now only 210 left. Okay, so notice how we have several possible variables here. We can select how big of a size of a packet to send, and usually TCP sort of receives some data into the socket until a certain time has expired, and then it can choose to send the packet out. Okay, so this size is picked dynamically to not cause the receiver to wait too long. Yes?
So the queue seems like it's per connection, right? Not like
Yes.
globally. Okay.
So this queue is per connection. Okay, and you could say that in some sense this queue is directly associated with the receiving socket. Okay. Now, here's another instance here where we send it sequence number 230, okay, size 30. We get back this ACK of 190 and 210. So what happened here? Well, what happened here was presumably I sent this chunk, but it never actually arrived at the destination. So here's a lost packet of size 40. Sequence number 190 didn't show up. I, as sender, kept going, and now the sequence number 230 of size 30 showed up. And notice the acknowledgement's a little different here, right? Somebody explain this acknowledgement to me, 190, 210. Why is it the same as the previous acknowledgement? Yes?
Because it's in order, that means that you never receive the next byte after that one. So those are the transfer to one that follows that.
Yeah, all it's saying is I've only received all of my data up to sequence number 190. And after that sequence number, there's 210 left. Notice it did not acknowledge this packet. Okay, can somebody, does this make sense? Okay. Now notice at this point, we've got a bit of a problem, because eventually we're going to have to get this chunk of data, and we're going to have to decide whether we need to retransmit this or not. So let's keep going. So presumably the source keeps sending, and here's a case. Notice the acknowledgement hasn't changed. Okay? And at some point, we get a timeout. And at that point, we know exactly what to retransmit. Why do we know exactly what to retransmit? Because the acknowledgements are telling us what data it got. It got data at sequence number up to 190 is the last thing that was transmitted. So the sender knows that it was this packet that was lost. Okay? Now, notice what the acknowledgement did at this point. It says, oh, good, I've received everything up to 340 and there's only 60 bytes left. Okay? So this is kind of a self-adapting protocol that basically tells you where the first hole is in my reception. The problem you can imagine is if we've got a lossy situation and there's more than one hole, we actually have to go through a timeout period for every hole there is in what I've received. Okay, because of the way the original TCP/IP protocol is constructed. Yes?
But it keeps sending, if it's multiple holes, it keeps sending on top of the window as it waits for the next time, right?
It will actually, potentially, it will keep sending beyond the window up to a point at which the timeout happens, and then, yeah, then at that point it'll start retransmitting things potentially over stuff it's already gotten, except if the acknowledgement tells it it's okay. So in this instance, this one hole fill immediately allowed the destination to acknowledge everything up to 340, and it didn't have to retransmit any of this other stuff.
So say like it sends 190, would it like, and then before it got the ACK back for that it got 190, would it keep sending 340 for
Yeah, so that's a great question. Depends. Okay, it depends on the TCP implementation because there's several things you could imagine. One is optimistically send a bunch more, assuming that things were lost in a burst. Then we have the potential for a lot of wasted sends. But in those instances, we can certainly get rid of duplicate packets because we know what's duplicate and what isn't, right? The other is to just wait until you get the ACK back and make some decision, all right? And different protocols do different things. Okay. And so finally, at this point, we can transmit the last couple of pieces. And notice at this point, we're acknowledging up to 400, and there's 0 left in the queue. What happens now? What happens? Anybody? Can we send any more data? Why not? Buffer is full at the receiver. This is a case where the window is completely shut down and we will not send any more. Okay, now how do we start opening the window? Well, at that point, the receiver, the process that's receiving, has to start sucking things out. And at that point, we'll actually get an acknowledgement back that looks more like 400 / and then 20 or 40 or 80 or however much the receiving process took out, at which point we know, oh, gee, we're receiving data again. There's space at the destination I can start sending. Okay, yes? Oh, this is the TCP portion of TCP IP. So the question is, does the TCP layer hand packets off to IP one at a time or in groups? So again, depends a lot on implementation. Because think of IP and TCP are different layers in the stack, right? So IP is layer 2, it's the network layer. TCP is a higher layer, layer 3. And in that instance, the software can explicitly reflect the layering, in which case the TCP is handling packets one at a time to IP, which is then doing something with them. Or it can be sort of squashed together for more efficiency in some implementations, and that's totally dependent on software. It's a good question. Yes?
So once you get to the point of the 400/0, then how does this receiver indicate to the sender that it'll like process some of those packets and make room to how does it let the sender know about that?
What happens is it'll start sending ACKs that say 400 / something non-zero. Yeah. Okay. So this is why, by the way, you can use TCP to do something like telnet into something, which I told you guys never to do, or SSH into something, and you type one at a time, and each character, can go to the other side. Or if you send a lot of characters, it doesn't matter whether the buffer fills up or not, because this system will explicitly make sure that every datum that goes in can be received at the other side, and it'll be received at the other side. So it's a pretty good protocol. Question? Yes.
So what you said, to answer this question, are you saying that you could have potentially more acknowledged than requests?
Yes.
Okay.
So you can have acknowledgments afterwards, and let me just show you why. I'll show you why that is in just a second.
Oh, all right.
So in other words, so the answer to your question is you do not have to have an outgoing packet to receive an incoming ACK. Okay, good. So some administrivia, project for design document. I've decided to extend until Wednesday. Based on popular demand. So anyway, you can wait until midnight on Wednesday if you like, and you're okay. The exam, of course, is coming up. It's on 12/16 in 10 Evans. It's all the material from the course, excluding the last day, and slightly more focus on the last half, but probably definitely will include material from the whole course. You get 2 sheets of notes, both sides, and a dumb calculator, so no cell phones, iPads, anything that's got a network connection or a cellular connection, or if you have a wire going between your desk and the person behind you, that's probably not allowed. Yes?
Is it TI-AD
So if it's a TI something or other that you can show doesn't have a network connection, you're probably okay. Okay, it's okay if you want to take your simple arithmetic we ask you to do and graph it. You're more than happy to allow you to do that. All right, any other questions? Okay. Design review. Oh, so the design reviews are Monday and Tuesday, as usual, after Thanksgiving. So hopefully your TAs have already set those up. I don't know. Are we all set up for design reviews? Oh, yes, they will set them up tonight or early tomorrow. And then, so you guys should probably sign up for your design reviews before going away and eating too much and falling asleep for Thursday and Friday. But yeah, the design reviews will be Monday and Tuesday. Okay. There is a lecture on Wednesday. Woo! Including this one, we're down to actually 4 lectures, so except for the last one, which is optional. And fortunately, I've now got lots of suggestions for the final lecture. Thank you, thank you. I'm now at the point where I'll have to start pruning, although if you really have some other suggestion you'd like, please send them. I haven't started pruning yet. So probably Monday after Thanksgiving, I will mention the list of topics that I got and which ones I chose, or if there's a couple I'm having trouble deciding on, I'll let you guys help me with it. So feel free to send me up until, how about up until Thanksgiving, you can send me suggestions for the final lecture. All right, any questions on Administrivia? So, let's talk a little bit about acknowledgments in TCP. So what's kind of interesting about TCP is if you look at the header has a sequence number and an acknowledgement number. Okay, so it's a sequence number that's part of the outgoing connection and an acknowledgement number that's part of the incoming connection, and those are on every IP packet. What that means is anytime you send a packet, you can also be acknowledging receiving packets. Okay, so the reason they did TCP this way is that it allows you to, for instance, hold off acknowledging for a little while you're receiving stuff to reduce the number of acknowledgments. Okay, so in fact, you don't even have to send an acknowledgement for every incoming packet. Or, if in the case of the window opening up we mentioned earlier, you can send acknowledgments that didn't respond to an incoming message. Okay, so these go in both directions, and so you're simultaneously acknowledging and potentially sending in every packet. Okay, questions? Now, as I mentioned, there is this slight problem of what to do when failures happen. Okay, yeah, you can retransmit the whole, but then the question is, do you start sending other stuff, or do you wait till you get the acknowledgement to see exactly what the next thing is you want to send? That was exactly what was asked earlier. And the answer is, well, either you wait and therefore lower bandwidth and don't respond to failure well, or you send a bunch of stuff potentially causing more congestion, causing more problems. Okay, so that's enough of a concern in modern TCP/IP networks that there is an optional thing called selective acknowledgement, which uses the option field of TCP to basically say something about exactly where the holes are and what's received. I'm not going to talk about this more, but it was available in Windows since about Windows 98, so it's been around a long time. I say here that it's not widely in use, but I actually think that that's probably a lie now. It's much more widely in use than it was. It's increasingly so, and however, it's part of the negotiation at startup. So when you start up a connection, you have to say whether the other side knows about selective acknowledgement or not. Okay? And it's really about being able to say exactly which packets are missing, exactly which byte ranges are missing, so that the transmitter can transmit exactly what's missing and then get onto it and start transmitting new data. Okay, any questions? Okay, so you can look up selective acknowledgement, by the way, Google it, and you'll see a lot more about what it's about. So let's talk a little bit about congestion avoidance. So we said earlier that TCP is a good citizen. What that means is it tries to reduce the rate at which data is going into the network to avoid losing packets in the middle of the network. And the loss of packets because a router is overloaded is called congestion. And it's really about deciding how long should the timeout be and how much data should you have outstanding between acts. So how about how long the timeout should be? Well, if it's too long, you actually end up wasting time if the message is lost. So if you wait 2 days to retransmit, then clearly the moment you hit a hole because the packet was lost, now you wait 2 days and then you retransmit. So clearly a long timeout is a very bad idea. Okay. On the other hand, a short timeout is also a really bad idea because if you send a packet off and it hasn't even made it to the destination and there hasn't been any chance for the ACK to get back, and then you retransmit, what have you just done? Well, you've sent 2 packets or 4 packets and you've increased congestion and increased the chance that you're going to lose packets in the network. So setting this timeout to be just right is a very important thing. It's very important to the performance of TCP. Okay. Can anybody tell me how you might figure out what a good timeout is? Yeah.
Proportional to the number of hops in the queue.
Okay, you might try to compute the number of hops. Okay, what else?
Proportional to the round trip time.
Yeah, probably more proportional to the round trip time would be better than the number of hops because you don't really know how long each hop is. Okay, now of course you don't want it to be exactly one round trip time because, well, it varies, right? Yeah, go ahead. Yeah, so exactly right. So the timeout is tunable. Basically what you're doing is you're observing round trip times and you're selecting your timeout to be related to the round trip time. The question is how much related? Well, oftentimes it's a factor of 2 or a factor of 4 round trips is the number you pick because that's a pretty good balance between wasting time when you lose packets and increasing congestion. Okay? Now, and basically this is the stability problem. Okay, more congestion, you delay your ACK, get a timeout, more traffic, more congestion, etc. And notice also that in addition to the timeout, it has a lot to do with how much data I shove into the network. So we want to tune the window size. So how do we choose the window size, which is the number of datums that I allow before I see an ACK? Okay, well, clearly it's got to be less than the receiver's advertised buffer size. Okay, why is that? Well, I want to make sure I never send data out that could be dropped at the destination because there isn't enough buffer space. I'd like to try to match the rate of sending packets with the rate of the slowest link. So if I send packets very rapidly because I got a really fast link and then there's a 96 kilobit per second modem in the middle, the only thing that's going to happen is I'm going to send so much stuff and right at the point where that modem ties in, I'm going to fill up the buffers and overflow, and I'm just going to end up dropping packets. Okay, so clearly I want to make sure that my rate matches the slowest part of the network. And basically the sender uses an adaptive algorithm to decide this. And it's really based on what we call the window size at the sender's window size, which is how much data in bytes do I allow outstanding before I see an ACK for those bytes. Okay? And the basic technique is pretty simple. I keep increasing my window until I start dropping packets. Okay, so I want to get somewhat on the bleeding edge of dropping packets, and then I know I'm kind of right at that point where I'm putting in as much data as can make it through at that rate. Okay, and TCP actually has a long history of tuning this algorithm. So there was an algorithm, the Van Jacobson TCP slow start was one of the first ones to do a really good job of this. And this is basically the notion that you start sending slowly. That's where the slow start comes in. So if there's no timeout, you slowly increase the window size, okay, by 1. Okay, now 1 what? Well, 1 unit, okay, bytes, whatever. And then timeout reflects congestion, and so at that point you cut the window size in half. Okay, so what you're doing is you slowly open the window up until you hit the point where things are lost, and then you go back to half size and then you slowly increase again. And what you see is you actually see this sawtooth behavior of bandwidth that TCP uses, and that's trying to make sure that you're not exceeding the point at which you're losing data, but you're kind of adapting ideally there. It's between sort of the halfway point and the point at which you're losing data. Okay, questions? So this is why, by the way, it takes a little while for TCP to kind of get up to speed, because it takes it a little while to kind of find that ideal transmission point. Okay. So as a final sort of topic here on TCP, we might ask, how do you get the right sequence number to start with? So you open a brand new connection. Do you start with sequence number 0? Okay, well, no. And the reason is you don't know whether you have just closed a previous connection and there might still be packets in flight. And so by making sure that your sequence numbers are kind of in a unique part of the space, then you sort of avoid that problem. Okay, because if your sequence numbers are overlapping with a previous connection, then their whole use is kind of suspect. And the other thing that's kind of interesting is if it's possible to predict the sequence numbers, it's actually possible to hijack TCP connections. And there have been some instances of this where somebody figured out how to predict what sequence numbers were being used with new connections, and they were able to send the right set of packets in to actually hijack a console session and actually break into a bank one time. So there was a couple of interesting kind of uses of predicting of sequence numbers. So this sort of leads you to want to make sure your sequence numbers are A, unique, and B, not predictable. Okay, so some ways of choosing the sequence number. One is, so this is about the uniqueness. You might somehow have it related to time to live, so you know the packets are truly gone and you're always above any range of, or unique from any range of packets that might be around. And if you sent packets X seconds ago, you could assume that they're definitely no longer in the network, and it's okay to reuse those sequence numbers. So that would be a uniqueness idea. Another might be some sort of epoch thing, which basically uniquely identifies sort of which sequence numbers are currently in use. And so you sort of have part of the sequence space is epoch numbers, and the other part is sequence. That's not used too much. The third one is a pseudo-random choice, which is used. All right. Questions? Now, so we have TCP. How do we use it? So popping up a level, there's this notion of sockets, which, as I mentioned before, showed up with BSD 4.2 for the very first time. It was an abstraction of a network I/O queue. Okay, and it basically embodies a single side of a communication channel. So it's the endpoint, it's got queue space, and it's all about binding two sockets together so that at that point, and saying that they're the TCP protocol, so that at that point you put bytes in on one side and they show up on the other side. And so really communicating with sockets is about allocating the sockets to either side, connecting them together, and then using them. And what's interesting about the socket interface is it's the same interface for sending and receiving data regardless of whether the socket's in China or on a machine in the machine room locally or on the same machine. Okay, so you can get what are called Unix sockets, and what a Unix socket is it's a socket that's in the file system and is purely used to communicate between two processes on the same machine. Okay, it's the exact same interface, but it's the Unix socket protocol. There's no network involved. Or you can have a socket that's literally over the network. It's connected via TCP, and at that point, it's a network socket. Okay, question? Yes?
If you open an TCP socket to localhost, will it just create a Unix socket and or will it actually?
It'll actually probably open a real networking socket, but localhost tends to bypass a lot of the layers of the network, so it doesn't go through windowing or anything.
What are the performance ramifications of that?
Couldn't tell you offhand. It's kind of a question of how well you need to optimize round-trip local communication or not. It's a good question. I don't know the exact answer. I suspect it's extremely dependent on operating system. So these were first introduced in 4.2 BSD. Sockets have been around probably for most of your awareness of computers, so you could think of them as having always been there. So let's talk a little bit about how to use them, just so you get a flavor for the interface. So let's suppose we're building a client-server scenario where we've got a server, which is a web server on one side, and we've got a client, and it's going to connect. So what's the server do? Well, the server sets up what's called a server socket, where it creates the socket. There's actually a system call to create your socket. It binds it to the TCP protocol, gives it a local address and port. Okay, where local address now is, say, the local IP address and port of the server, and port is a well-known port number like 80 for the web server. It calls the listen system call, which basically tells the server socket to start accepting incoming requests. And then it basically, in a loop, performs multiple accept calls. And an accept call, unlike what you have to do for Project 4, an accept call in Unix is actually blocking. And so the server can go to sleep on accept, and it'll only wake up when there's a new connection for it. Okay? And each successful accept returns a new socket. So basically, you set up the web server socket, and every incoming connection will generate a new socket and hand it up via an accept call, and the web server can choose to either fork that off as a separate process or thread or do whatever it wants to with it, but it's a separate connection. The client side is pretty easy. It creates a socket, binds the protocol, TCP, the remote address and port, which presumably match the address and port of the server, performs a connect, and that will actually cause the connection to get set up. And when the connect is successful, then we have two sockets and we can communicate. Okay? Now that's a lot of words. I can show you a picture here, which probably helps a little. The things to remember are a connection has 5 values to it. It's a 5-tuple. It's a client address and port, a server address and port, and a protocol. That together is a unique connection. The client port is often randomly chosen, okay, done by the operating system when you set up a client socket. The server port is usually well known, like 80 for the web server, or 443 for secure web, etc., 25 for SendMail. And the well-known ports are in the range 0 to 1023. It's just the way it is. And so here is a picture. So notice that the server socket got set up originally, and it's kind of a funny socket. You never actually communicate through the server socket. All it is it serves as a setup point for incoming connections. That server socket is sitting there when a client socket sets up and requests a connection. And at that point, the server socket will return from accept with a brand new socket whose sole job is to be the endpoint connected with this new connection. And every incoming web client causes this to happen. So there'll be a brand new socket created on the server for every incoming connection. Okay? And then once we've got the 2 green sockets, we just communicate both directions, TCP. Question, yes?
So is the new socket on the server like just a randomly generated port also? Or?
No, the socket on the server actually has the same port and IP address as the server socket. But notice that it's connected to this other end. So as a connection, it's got this unique 5-tuple. Okay? So a socket by itself that's not connected to something doesn't necessarily mean something, except for a server socket, which can kind of sit there and wait for requests to come in. There was another question? No? Okay. Does this make sense to everybody? Question, yes? Okay, never mind. Okay. Now Java makes it really easy to set up sockets. So if you were programming using a C or C++ interface, there's a lot of steps I said here. So you create the server socket, you got to bind an address to it, you got to call listen, which effectively causes it to wait. Then you do a bunch of accept calls, and each accept call returns you a new socket on the server side. In Java, they've actually set some of that up for you. So for instance, the server code looks something like this. New server socket gives it the port 6013. Implied in this, of course, is the address is the local address. Okay? That returns a server socket, SOC. And now, this also, as a part of creating the new server socket, also calls listen. So basically, a lot of those steps I gave you on that 2 slides ago are all done by this one creation operation where you say, create me a new server on socket 6013. Okay, and it automatically binds the local address, this port, calls listen, and we're ready to go. And now in a loop, all we have to do is this. We say, execute socket.accept, sock.accept. This is blocking until somebody has actually tried to set up a connection, in which point I get a brand new socket out of this. And then I can do like this. I can sort of wrap a print writer around it, whatever. I can print to it. And I can close it, and I can loop back and get a new socket. Okay, very simple. Now the problem with this server is what? What's kind of brain dead about the server I just put together here? Yeah. Well, let's say that dropping the connection's okay because I've done what I've had to do. Yeah. It only handles one connection at a time. So if we really wanted to, if this operation were complicated, like a web server operation or something, what we'd really want to be doing is either taking these sockets and putting them on a queue where a thread pool is busy pulling things off, or we could fork off a new process for every incoming connection, although that's a little expensive. But you can see how we could put parallelism in this by letting lots of things act on the socket once it's accepted. Yes? Yes. So you're saying, okay, so you start with each socket has its own queue. So you're talking about once everything's established, when data comes in, what happens? Yes. So what happens there is the TCP/IP layer looks at the 5 tuple of an incoming packet, and it says, oh, I know that that goes to this socket or that socket or that socket.
Okay, and then that data then give that socket.
And it goes to the queue of that particular socket. Yes. Yes. That's exactly right, to decide whether to drop it and also what to do after that. Probably wouldn't drop it, though, hopefully, because of the mechanisms we said earlier. Okay? So yeah, so that demultiplexing layer is, in fact, an expensive part of TCP/IP because it's got to look at the header and decide sort of which socket an incoming packet goes to. Yeah, everything can have a queue. It's a question of how fast you can do it. But in principle, all you're really doing is taking incoming packets that are part of established sockets, sorting them by their 5 tuples, sending them to the right socket endpoint, and then they're getting queued there. And that's the trick is to do that as fast as possible. So let me just show you the client side of this. Here, we actually have to say what the IP address is as well as the port, because this is presumably a remote IP address from the client. Here's the same port. Okay? We get a brand new socket. At this point, we can wrap input stream readers, whatever, around them. We can read line them. We can print out the result, the standard out, and then close our socket. And effectively, what we've done is once we've set this server up, then we can run a bunch of these clients, and they'll all get back, here is data sent to the client. Okay? So it's kind of a boring example, but it gives you all the pieces required for this communication. Okay? Questions? All right, so let's take a break. We're running a little bit late, and come back. right. Okay. So there's one thing that, so I had a good question. Let's close our laptops again. I had a good question over the break, which I did want to make sure was clear here. Sockets are just endpoints, and they don't have to be bound to TCP. I think I said already that they could be bound to what's called a Unix socket, where the communication is through the file system. They can be bound to TCP if what you want to have is a stream in and stream out, or they can be bound to UDP, in which case what you write a chunk of stuff to the socket on one side, and it comes as a packet to the other side, and comes out as a chunk. All right, so you can actually you actually have to set up sockets to do UDP communication as well. So let's move on a bit now to how we might use this. So how do you actually program a distributed app now that we've got something like TCP? And among other things, we need to synchronize multiple threads running on different machines. If you remember back when we were talking about synchronization on a single machine, since we had shared memory as one of our assumptions, then we could build locks and semaphores and monitors and all that sort of apparatus to synchronize between two processes that were on a single machine. The problem when you've got a distributed application where a process on one side is communicating with a process on the other is you can't necessarily use shared memory to communicate. And so all the locking mechanism is broken. And so we got to come up with something else. Now, fortunately, messaging kind of gives us the ability to build that something else pretty easily, which is a packet or a message. I'm not going to use the word packet. Sent from one side can arrive at the other side, and it simultaneously has data and is a synchronization with it because it says, hi, I'm here, here's the data. Okay, so you can actually build algorithms that are distributed in nature that make use of the atomic send-receive of messages and sort of use that to build synchronization primitives and communication primitives and so on. Now, so the messages are already atomic. There's never the case that part of a message is received or not received at all. And how can I say that? Well, because we're building this on top of, say, TCP. So I'm talking a layer higher than TCP now. Okay. So what's the interface? Well, this interface might be something like a mailbox, which we could think of as a temporary holding area for messages. Now, a message is a chunk of data that's sent as a group. It includes, in the case of a mailbox, you could say it might include both destination and queue. Okay? And so there'd be a mailbox at this destination side. And when I send to that mailbox, I'm sending to a particular mailbox and a particular queue. So the interface might be this: send message to a given mailbox. Now, given what I told you about TCP/IP just a moment ago, how do I describe a typical mailbox in a TCP/IP scenario? What do I need for information? Now remember, I'm just sending to a mailbox, so I know there are people that want to say the 5-tuple, but you don't need the whole 5-tuple to say send to a destination mailbox. What might it be? Yes? Yeah, a destination address and a port, where the assumption is because we're doing messaging, probably the TCP is assumed, and we pick a random port at the source side and so on. So basically a mailbox is really just an IP address and a port, maybe in this case. Okay? And receive would be something like, here's a buffer received from this local mailbox. And this could be blocking, or it could be non-blocking. If it's blocking, potentially you don't return until there's a message there. If it's non-blocking, maybe you return and say there's no message. Okay, so this is a very simple interface we can build right on top of TCP. And then what could we do with it? Well, we could start building distributed applications with it. Okay, so we might ask some semantic questions like, should send return right away? Okay, so basically the message is buffered locally and then send returns. Or should it wait until the receiver process actually absorbs the message? Okay, those are two completely different types of semantics we could ask for. Does everybody see the difference? One is send, oh, yep, I had queue space locally, I'm done. That's quick, but you have no idea, A, whether it makes it to the remote machine before it crashes, or B, whether it makes it to the remote machine and then up to the process that's talking. Okay? So we could have some possibly different semantics here. So what about this? So the two questions we're really asking is, when can the sender be sure the receiver actually received the message, and when can the sender reuse the message, reuse the memory containing the message? And so these are questions we can ask depending on what our send and receive are. But Mailbox ultimately provides a one-way communication from some thread to some other thread with a buffer in between. Very similar, you could actually say, to what we had with producer-consumer, where send was sort of a V operation, receive was a P operation. And in this case, we don't really know whether the sender and receiver are local or not. So by putting a network abstraction underneath us and building on top of that, we can truly get location independence. And when we talk about remote procedure calls, which I don't think we'll get to until next time, and distributed file systems and so on, we really don't know whether we're talking to something locally or remotely, and maybe it doesn't matter other than a latency factor. Okay, whereas when we were really, dealing with synchronization earlier in the term, we knew it was local, because that was the only option. So, using send and receive for producer-consumer style. Remember, we did this producer-consumer with the Coke machine example. So here, we might do something like this. While one, we prepare the message we want to send. We do send message 1 to mailbox, and this is producing messages which go across the network. And all the receiver does is it has a receive buffer. It says receive from the mailbox, process it, and does that in a loop. And this is self-synchronizing because, why? Well, because the messages get sent exactly once because of TCP semantics, for instance. If there's no space because the buffers are full at the receiver, the sender will stop. Okay, remember how we set up TCP to stop? And so this is a self-synchronizing producer-consumer that goes across the network. Okay, and so there's really no need for the producer or consumer to keep track of the space in the mailbox, because that's really handled underneath by TCP/IP, or you could say it's handled by the send and receive abstractions. Okay, questions? Now, what if we want to do two-way communication? Well, we need two mailboxes, one on either side. Okay, and for instance, here's an example. This is called client-server, in case you're not familiar with it. Here's an example of a file service. So on the client, we sort of send a read request to the server mailbox, and then we receive from our local client mailbox a response. This is really saying read the file rutabaga, and I get the response back. And gee, this is very simple, just using my send and my receive primitives to do that. Now, presumably, I've set up these server and client mailboxes in advance to make this work. And what's the server do? It basically receives the next command, possibly with a blocking receive. It decodes it, reads the file into the answer, sends the answer back, and we're good to go. And there you go. There's a distributed file system. Okay, now there's a few more details, which we'll have to talk about next time, but you get the idea. Okay, very simple, synchronized producer-consumer application. Okay, questions? Yes?
Does the send and receive share the same socket?
So, doesn't have to. The question is, does send and receive share the same socket? So at this level of abstraction, perhaps I don't tell you that. Doesn't, maybe at a lower level of abstraction, we would cache socket connections with the other side for efficiency reasons, but at the level of programming it sends and receives, you don't really care. Okay. And when we get to remote procedure calls, there isn't even a question about sockets anymore. I mean, it's literally you're making a procedure call and it happens to get ferreted off to the other side, comes back, and it works. Okay, and so there you really don't know whether sockets are there, how they're used. Okay. So let's talk about some interesting messaging things to leave you thinking for tonight. So first of all, let's talk about the generals paradox. Okay, so the constraints of the problem are the following. Two generals, they're on separate mountains. They can only communicate via messengers, which are effectively messages. And the problem is messengers can get captured. Okay? Now, problem, need to coordinate the attack. If they attack at different times, they die. If they attack at the same time, perhaps they live, okay? Now, of course, this is named after Custer, okay, who died at Little Bighorn because he arrived a couple days too early. Okay, now, this is no endorsement of Custer, by the way. This is just where this comes from. So, what's the paradox? So, can messages over an unreliable network be used to guarantee that two entities do something simultaneously? What do you think? How many people think yes? Okay, how many people think no? How many people don't know? Okay, the answer is actually no, and the key word here is simultaneously. The important point here is time. Okay, so, and it's true even if all the messages get through, and the reason it can't be done even if all the messages get through is because you need to assume the possibility that a message didn't get through. Okay, now let me give you a good example. Dun, da, da, da. Oh, 11 okay? Is 11 a.m. okay? Yeah, 11 works. So, 11 is it? Okay, yeah, but what if this one's lost? Okay, so the problem is, at no point do both of them know for sure that they both agreed to go. Right? Because this one asked about 11, he says 11 works, but at that point, he doesn't know that his message about 11 worked, so he's got to wait to hear from this guy. And he says, yeah, I did get your message about 11, but now he's not sure that his yeah, I got it worked, so you got to wait for this one to send back and so on. So you can see the paradox here. Okay? And the problem is that we're trying to agree about an exact time, not to agree that we're going to do it eventually. Now, of course, modern technology would use a radio, which kind of leads to very efficient communication very rapidly. Okay? But assuming we're stuck with messages, then this is a paradox. So, no way to be sure the last message gets through. So what can we be sure of? And the answer is, well, we can be sure that something will happen eventually. And this leads to the notion of two-phase commit. How many people have run into two-phase commit before? Anybody? A couple of you? Okay, so the idea is the following. We can't solve the general's paradox, and so we're going to solve a related problem which says two machines agree to do something or not to do it atomically. Okay, and what it means to agree to do something is that they will eventually do it. And two-phase commit protocol has been set up exactly to do this. And the idea is we use a persistent stable log at both sides to keep track of whether the commit has happened. And then if a machine crashes, it can come back up and check the log to see whether it can recover the state of the world after the time of the crash to make sure that if it made a promise to do something, that it will do it. And if somebody else made sure that nobody does it, that nobody does it by accident, okay? And so there's two phases, surprisingly, given it's called two-phase commit. The first phase is the prepare phase. And here the global coordinator requests that all participants promise to commit or to abort. So participants basically put a little mark in their log saying that there was this request, and then they acknowledge. Okay, their little mark in the log is whether they decided that they're going to say yes or no. So then they acknowledge. If anybody votes to abort, the coordinator writes abort in its log, tells everyone to abort, and nobody does anything. On the other hand, after all the participants respond with yes to commit, notice at the point that the coordinator gets a yes from everybody, they have all written in their logs that they've promised to do it. And therefore, if anybody crashes before actually doing it, they still know they promised. Okay, and what happens here is that the coordinator writes commit, which effectively says, I received commit from everyone, and then it tells all the nodes to commit. And they will eventually acknowledge, and we're good to go. And the point is, these logs, if you do it correctly, can be used to reconstruct the state of the system such that everybody either agrees and does it, or disagrees and doesn't do it. There's no situation where some people do it and some people don't. Yes? Well, you can. The problem, though, is let's take that exact example here. Suppose that I am somebody who's agreed that I will attack at 11, and I put a commit record on, and then I crash. Right? The problem is that I can eventually do it, but it may be that I only come up after 11 a.m. Okay, so the problem here is really that I can't be sure of the simultaneity. I'm losing it tonight. But I can be sure that it'll eventually happen. Okay? So here's an example. So suppose A is Wells Fargo, B is Bank of America. Phase 1 is the prepare phase, where A writes begin transaction to its log. A sends to B saying, is it okay to transfer funds? B maybe says no, in which case A writes abort to its log. If there are enough funds, B says yes and puts a promise to commit to the log and says, okay, I can commit. Phase 2, A decides for both whether they will commit or not. Okay, basically based on the information, writes a new balance to the log and the word commit. And then it tells B to commit. And it waits for an ACK and eventually gets got commit back after the ACK. So we can go through this, and I don't want to do this extensively, but you can cause a crash at any point in this process, and you won't violate this notion that people either all do it or nobody does it. Okay, so for instance, if B crashes at the beginning, basically it wakes up and does nothing. A times out, aborts and retries, so nothing was done. A crashes at the beginning of phase 2. It might wake up. Notice there's a transaction in progress. Send B to an abort. B crashes at the beginning of phase 2. B comes up, looks at the log, sees that it had already promised to commit. When it gets A's commit, then it will. Okay, so basically you can work through a bunch of scenarios, but what's nice about this is it has that atomic property to it. Now, we can think of two-phase commit as, in general, a case of distributed decision making, and the question is, why is this useful? Well, one reason is fault tolerance. If they all agree, then it's good. If people don't agree, then it's bad. Okay? So you can have a group of machines coming to a decision even if one or more of them fail during the process. And this is why people are interested in distributed decision making. And the simple failure mode that they typically talk about is fail stop, where somebody who fails doesn't do something arbitrarily complicated. Okay? And after the decision's made, the result is recorded in multiple places, and so you don't lose the fact that you decided to do something. Okay? Now, two-phase commit is very simple and primitive. So an undesirable feature of two-phase commit is blocking, which basically, for instance, you could go through this scenario where B says prepared to commit, and then A crashes, and B can't come up because it's already said it will commit, but it's got to wait for A to tell it to commit before anything can go forward. And so B is stuck on A. Okay, and two-phase commit basically can be completely held up if one of the machines is in a transient dead state. And so there is, of course, three-phase commit, which has one more phase and basically can deal with somebody not being currently online. Okay. So what we'll talk about next time is a more interesting problem, to me at least, which is if we're talking about nodes crashing and coming back up, that's maybe a bug, but it's not malicious. What's more interesting is what if you have one or two or more of the nodes are actually trying to maliciously mess up the scenario? And then when you go through a protocol and you try to say, well, suppose that half of the nodes or some fraction of the nodes are actually malicious, can they cause the group to do something that is incorrect? That's the notion of maliciousness. And we'll talk about the Byzantine generals problem next time, which is a way of solving this where as long as less than a third of the nodes are malicious, you can actually come to a good decision, even if they do their best to screw the protocol up. All right, so in conclusion, we've been talking about TCP, which is a reliable byte stream between two processes on different machines over the internet. Okay? Uses Windows-based acknowledgement protocol, congestion avoidance, dynamically adapts sender window to account for congestion. We talked about two-phase commit, which is a distributed decision making. We're going to talk about the Byzantine generals problem next time, which is a distributed decision making process which works even when you have nodes that are malicious, which is quite interesting. So you have a good couple of days. I guess before I see you next time, you won't have to have turned your project design docs in. So breathe a little more easily. Talk to you later.